Peak detection in a 2D array. I'm helping a veterinary clinic measuring pressure under a dog's paw. I used Python for my data analysis and now I'm stuck trying to divide the paws into anatomical subregions. I made a 2D array of each paw that consists of the maximal values for each sensor that has been loaded by the paw over time. Here's an example of one paw, where I use Excel to draw the areas I want to detect. These are 2x2 boxes around the sensor with local maximas, that together have the largest sum. So I tried some experimenting and decided to simply look for the maximums of each column and row. Can't look in one direction due to the shape of the paw. This seems to detect the location of the separate toes fairly well, but it also marks neighboring sensors. So what would be the best way to tell Python which of these maximums are the ones I want? No, the 2x2 squares can't overlap, since they have to be separate toes. Also, I took 2x2 as a convenience. Any more advanced solution is welcome, but I'm simply a human movement scientist, so I'm neither a real programmer or a mathematician, so please keep it simple. Here's a version that can be loaded with np.load. Results. So I tried a JXT solution. See the results below. As you can see, it works very on the front paws, but it works less well for the hind legs. More specifically, it can't recognize the small peep that's the fourth toe. This is obviously inherent to the fact that the loop looks top down towards the lowest value, without taking into account where this is. Would anyone know how to tweak a JXT's algorithm, so that it might be able to find the fourth toe too? Since I haven't processed any other trials yet, I can't supply any other samples. But the data I gave before were the averages of each paw. This file is an array with the maximal data of 9 paws in the order they made contact with the plate. This image shows how they were spatially spread out over the plate. Update. I've set up a blog for anyone interested and I have set up a OneDrive with all the raw measurements. So to anyone requesting more data, more power to you. New update. So after the help I got with my questions regarding paw detection and paw sorting, I was finally able to check the toe detection for every paw. Turns out, it doesn't work so well in anything but paws size like the one in my own example. Of course, in hindsight, it's my own fault for choosing the 2x2 so arbitrarily. Here's a nice example of where it goes wrong. A nail is being recognized as a toe and the heel is so wide, it gets recognized twice. The paw is too large, so taking a 2x2 size with no overlap causes some toes to be detected twice. The other way around, in small dogs it often fails to find a fifth toe, which I suspect is being caused by the 2x2 area being too large. After trying the current solution on all my measurements, I came to the staggering conclusion that for nearly all my small dogs it didn't find a fifth toe, and that in over 50% of the impacts for the large dogs it would find more. So clearly I need to change it. My own guess was changing the size of the neighborhood to something smaller for small dogs and larger for large dogs. But generate_binary_ structure wouldn't let me change the size of the array. Therefore, I'm hoping that anyone else has a better suggestion for locating the toes, perhaps having the toe area scale, but the paw size?
I also ran it on the second dataset of 9 paws and it worked as well. Here is how you do it. All you need to do after is use scipy.image.measurements.label on the mask to label all distinct objects. Then you'll be able to play with them individually. Note that the method works well because the background is not noisy. If it were, you would detect a bunch of other unwanted peaks in the background. Another important factor is the size of the neighborhood. You will need to adjust it if the peak size changes. This should remain roughly proportional.
Solution. Data file, paw.txt. Source code. Output without overlapping squares. It seems that the same areas are selected as in your example. Some comments. The tricky part is to calculate sums of all 2 by 2 squares. I assumed you need all of them, so there might be some overlapping. I used slices to cut the first/last columns and rows from the original 2D array, and then overlapping them all together and calculating sums. To understand it better, imaging a 3 by 3 array. Then you can take its slices. Now imagine you stack them one above the other and some elements at the same positions. These sums will be exactly the same sums over the 2 by 2 squares with the top left corner in the same position. When you have the sums over 2 by 2 squares, you can use max to find the maximum, or sort it to find the peaks. To remember positions of the peaks, I couple every value, the sum, with its ordinal position in a flattened array, czip. Then I calculate row/column position again when I print the results. Notes. I allowed for the 2 by 2 squares to overlap. Edited version filters out some of them such that only non-overlapping squares appear in the results. Choosing fingers, an idea. Another problem is how to choose what is likely to be fingers out of all the peaks. I have an idea which may or may not work. I don't have time to implement it right now, so just pseudocode. I noticed that if the front fingers stay on almost a perfect circle, the rear finger should be inside of that circle. Also, the front fingers are more or less equally spaced. We may try to use these heuristic properties to detect the fingers. Pseudocode. This is a brute force approach. If n is relatively small, then I think it is doable. For n equals 12, there are c_12 to the power of 5 equals 792 combinations, times 5 ways to select a rear finger, so 3,960 cases to evaluate for every paw.
This is an image registration problem. The general strategy is: have a known example, or some kind of prior on the data, fit your data to the example, or fit the example to your data. It helps if your data is roughly aligned in the first place. Here's a rough and ready approach, the dumbest thing that could possibly work. Start with 5 toe coordinates in roughly the place you expect. With each one, iteratively climb to the top of the hill, i.e. given current position, move to maximum neighboring pixel, if its value is greater than current pixel. Stop when your toe coordinates have stopped moving. To counteract the orientation problem, you could have 8 or so initial settings for the basic directions, north, northeast, etc. Run each one individually and throw away any results where 2 or more toes end up at the same pixel. I'll think about this some more, but this kind of thing is still being researched in image processing. There are no right answers. Slightly more complex idea, weighted, k-means clustering. It's not that bad. Start with 5 toe coordinates, but now these are cluster centers. Then iterate until convergence. Assign each pixel to the closest cluster, just make a list for each cluster, calculate the center of mass of each cluster. For each cluster, this is, some coordinate intensity value / some coordinate, move each cluster to the new center of mass. This method will almost certainly give much better results, and you get the mass of each cluster, which may help in identifying the toes. Again, you've specified the number of clusters up front. With clustering you have to specify the density one way or another, either choose the number of clusters, appropriate in this case, or choose a cluster radius and see how many you end up with. An example of the latter is mean shift. Sorry about the lack of implementation details or other specifics. I would code this up, but I've got a deadline. If nothing else has worked by next week, let me know and I'll give it a shot.
Using persistent homology to analyze your data set, I get the following result. Click to enlarge. This is the 2D version of the peak detection method described in this SO answer. The above figure simply shows zero-dimensional persistent homology classes sorted by persistence. I did upscale the original dataset by a factor of 2 using scipy.miscellaneous.imasize. However, note that I did consider the 4 pores as one dataset. Splitting it into 4 would make the problem easier. Methodology. The idea behind this quite simple. Consider the function graph of the function that assigns each pixel its level. It looks like this. Now consider a water level at height 255 that continuously descends to lower levels. At local maxima, islands pop up, birth. At saddle points 2 islands merge. We consider the lower island to be merged to the higher island, death. The so-called persistence diagram of the 0th dimensional homology classes, our islands, depicts death over birth values of all islands. The persistence of an island is then the difference between the birth and death level, the vertical distance of a dot to the gray main diagonal. The figure labels the islands by decreasing persistence. The very first picture shows the locations of births of the islands. This method not only gives the local maxima, but also quantifies their significance by the above-mentioned persistence. One would then filter out all islands with a too low persistence. However, in your example, every island, i.e., every local maximum, is a peak you look for. Python code can be found here.